Let's take a look at jump game, LeetCode 55. You are given an integer array nums. You are initially positioned at the array's first index, and each element in the array represents your maximum jump length at that position. Return true if you can reach the last index, or false otherwise. Okay, so looking at our first example, seems pretty clear. Each item in the array just tells you how far you can jump. So looking at this first example, we can do something like jump to this square because that's within 2 distance away, because it's just 1. So for our first step right here, we can either jump to the 3 or jump to the 1, right? We notice that jumping to the 3 works pretty well. We can jump straight to the 4, but jumping to 1 works as well, right? A few more jumps, but we can reach there as well. So we just need to return if we can reach the last index or not. So basically, the only way to not reach the last index, the only blocker is if you're stuck at a 0, right? So no matter how small the value is, so looking at our constraints, the min value is 0. So if it's 1, 2, there are no negative values. If it's 1, 2, 3, or 4, you can always move forward. But if you're stuck at a 0, that means there's no more moving forward for you, and then you're stuck. So another thing with looking at our constraints here, we can see that the length of our array, num.length, can be all the way up to 10 to the 4. So we probably want to solve this in linear time or something close to linear time. So kind of looking at this, the first thing to sort of note is making optimal jumps each time. So every time you jump, let's say you were to jump to this second square, right? If we go from here to the second square, we missed jumping to the 3. And the 3 could have brought us someplace further. So what we can do here is at each jump, we can simply make a decision, right? So we start at 0, so we can end up at 2 different locations. We can end up at 1 or 2. And all we really have to do is decide which one is better, 1 or 2, based on the furthest next point that it can take us. For example, at 2, 1 and 3, if we were to jump to this first index, the maximum distance this next index can bring us is 4. So it can bring us to the 4th index, right? But for the second index here, the maximum distance it can bring us is 3. So actually what this means is that it is always optimal to choose the one with the larger value, because there's no reason to jump to this 1 if we can jump to this 3 instead, and we know that this 3, say we jump to this 3, right? We jump to this 3. We can now jump to any one of these 3 next indices. However, if we contrast that to if we jump to the 1, right? If we jump to the 1, though we initially jumped further, we can only jump from the 1, we can only have that option here. So it is always optimal to be jumping to the index that corresponds to the largest index it's at plus the value at that index, because that will give us the furthest possible distance later. In that case, a solution is already pretty clear. You can just choose the maximum, iterate through whatever these. So in this case, if it was 2, you iterate through these 2, check, okay, 4. This is right, 1, 2, 0. So it's 4. So the first jump brings us to 4. The second jump brings us to 3, right? Because 1 plus 3, and then 2 plus 1. And then we see 4 is bigger, so we choose this one right here. And then same thing, after we've reached this location, we select from the next 3 Obviously here we've already reached the destination, and so we just sort of simulate this jumping process, and eventually we reach the end, and it's a very clear solution. So the problem is basically already solved like that, but there is a slightly better way we can do this as well without having to check. Because if we take a look at this solution, it is very possible that we have to check some values multiple times, right? Because there's a nested for loop. So let's say, for example, we have these numbers, right? We checked the maximum distance of 3 and 1 when we started at 2, of index 1 and 2, right? And then we chose this as our max. After we choose this as our max, we have to check all 3 of these again, which means we have checked this 1 2 times. And when the arrays are longer and bigger, it could be that we end up checking the same value a bunch of times, wasting runtime, right? Making our runtime slightly worse. So what we can actually do here is sort of implement a pretty cool trick. Rather than doing it like this, what we're going to say is instead, say we're working with these numbers again. At each time step, we're just going to keep track of one variable, and that variable is called max reachable distance. So what this means is this variable is just going to store the furthest place that we can go at any given time. So the current maximum reachable distance. The reason why storing this is so useful is if we take a look at this, we go through the same process, right? We look at this time, instead, we're going to just do one iteration, one for loop. Everything's going to be done in one for loop. So we're going to look at this. We're going to start from the left, go to the right, and we're going to say, okay, we start at index 0. We can jump to a distance of 2, which means our max reachable distance is now 2. And then we're going to iterate up to our next index. And we're going to be checking at every single index. Is this index less than the max reachable distance? If it is not, then we instantly return false, because that implies that this index that we're at, if it's less than the maximum reachable distance currently, that means that the maximum reachable distance is not going to get you where you want, right? It's not going to get you to this point. And if this index was less than this value, that means all of the indices over here, including the endpoint we want to reach, is also less than the maximum reachable distance. So it's impossible to ever reach where we want to go. So here, right, we are at 1 now. And we see that 1 is less than 2, right? Our current index is less than the maximum reachable distance. 1 is less than 2. And then what we do is we update the maximum reachable distance every single time we look at an item. So now we look at 3, right? We're like, okay, well now the maximum reachable distance is 4. So it's actually much bigger. So because, right, we're able to get all the way down to 4. And so we keep on doing this process and go all the way down. We check 1. We check this index. Okay, 2 is obviously less than 4. So this point can be reached. And we check. If this point can be reached, then what's the distance that it's able to reach? If we were to start at this point, that's just 3, right? We're able to reach right here. 3 is less than 4, so we don't update our maximum reachable distance here, right? So we keep on doing that all the way, and then we're able to reach the end. If we're able to reach the end, we're done. If we can't reach the end because our current index, we notice that our current index is less than the current maximum reachable distance, then we're also done. We return false. Otherwise, it's just true. Runtime, very straightforward. Time complexity is just O of n space complexity is O of 1, right? All we have to do is just store this one variable. That makes this problem very, very easy. And yeah, that's all there is to it.